All right, let's get right into it. You know, it's easy to think of a computer as just doing one thing, then the next. But that's not what's happening at all. Under the hood, it's juggling hundreds, maybe thousands of tasks, all at the same time. And to pull that off, it needs a system, an architecture really, for deciding what's most important right now. And that system? Well, that's what we're talking about today. It's called the heap.
And it all boils down to this one simple truth. Think about it. When you move your mouse, you expect that cursor to move instantly, right? That action has to be processed immediately. But what about, say, a software update check running in the background? Yeah, that can definitely wait a few seconds. No big deal.
And that right there, that's the core challenge of pretty much all modern computing. Every single millisecond, your operating system, your browser, even the router connecting you to the internet, they're all making a decision. It's this constant, super high-speed triage, figuring out what needs attention this very instant.
So, the big question is, how in the world do you build a system that can do that? A system that can sift through this constantly changing list of tasks and in a flash, pinpoint the single most critical one and do that millions of times a minute. How is that even possible?
Okay, so before we get to the really clever solution, let's talk about the obvious one first. I mean, if you need to find the most important thing, your first thought is probably, well, just keep everything sorted, right? Keep the whole list in perfect order all the time. Sounds simple enough, but it turns out that leads to a huge problem.
And here's why that's a problem. Imagine you have a perfectly sorted list of, 1,000 tasks. Then suddenly a new, super urgent task comes flying in. Now you've got to find its exact spot in the list and then shuffle maybe hundreds of other items down just to make room. That is a ton of work. It's total overkill when all you really care about is who's number one.
And this is where the heap comes in. It is such an elegant solution. See, a heap isn't just another data structure you learn about in a textbook. It's a brilliant piece of engineering, designed from the ground up to solve this exact problem with, frankly, ruthless efficiency.
And the key word you really need to latch onto here is partially. A heap doesn't even try to keep everything in perfect order. It has a much more focused goal. It just wants to make sure that the single most important item, whether that's the biggest or the smallest value, is always, and I mean always, sitting right at the top, ready to be grabbed at a moment's notice.
And for a lot of people, this is the real aha moment. The heap's superpower, its greatest strength, actually comes from what it decides not to do. By just completely abandoning the idea of perfect total order, it gains this incredible speed for managing the one thing that truly matters, whatever's at the top of the priority list.
This really gets to the core philosophy, the different mindsets. You know, a traditional search tree, it's kind of obsessed. It wants order everywhere. Every single node has to be in its precise sorted position relative to everything else. A heap? A heap is a total pragmatist. It basically says, look, I'm only going to guarantee one thing, that the item at the very top is the most important. Everything else, yeah, it can be kind of loosely organized. I don't really care.
And that's the trade-off, right? That's classic engineering. Heaps sacrifice that nice-to-have feature of complete order to get the absolute must-have feature. Incredible speed for adding new things and grabbing the top one. It's just a beautiful, elegant compromise.
Okay, so how does this partial ordering thing actually work? How does a heap pull off this magic trick of being just organized enough to be ridiculously fast?
Well, it really comes down to these two super simple, really elegant operations. First, when a new task shows up, you literally just toss it in at the very end of the structure. Then this cool thing happens, it bubbles up. It compares itself to its parent, and if it's more important, it swaps. It just keeps doing that, climbing the tree until it finds its proper level. And when you need the most important task, you just grab it. It's right there at the top, always waiting for you.
Now this is the part that computer science folks get really excited about. O of log n. That's the fancy notation for unbelievably fast, and it's the real secret to the heap's power. What it means is that the amount of work you have to do doesn't grow in lockstep with the number of items. For example, if you have 10 items, maybe it takes 3 steps to add a new one. Okay, but if you have 1,000 items, it might only take 10 steps. 1,000,000 items, maybe just 20 steps. The list gets massively bigger, but the work to manage it just barely budges. It grows incredibly slowly.
And that is the secret sauce. That bubble-up process we talked about, it's not resorting the whole thing. It just involves a few little swaps along one single path from bottom to top. It's like surgical precision instead of a massive overhaul. But here's the craziest part, the part that really blows my mind.
This whole tree-like structure we've been picturing, in reality, it's almost always just a simple, flat array in memory. There are no pointers, none of that complex stuff. It's all done with some clever math on array indexes to figure out who's a parent and who's a child. So it looks like a tree, but it acts like an array. And that makes it unbelievably compact and fast.
All right, so this all sounds great in theory, right? But where is this engine of urgency actually running in the real world? Well, the simple answer is pretty much everywhere. It is truly one of the most important and yet most invisible structures in all of modern tech. I mean, think about it. The CPU scheduler in your computer, it's using a heap right now to decide which of the dozens of programs you've got open gets the processor's attention in the next millisecond. The router that brings you the internet, it's using a heap to make sure the data for your video call gets priority over that big file you're downloading in the background. And you know when your GPS finds the fastest route home? That's Dijkstra's algorithm at work, and under the hood, it's using a heap to constantly ask, okay, what's the next closest place I haven't checked yet? It's the fundamental logic of what to do next.
So what heaps really do is they take this messy, chaotic idea of urgency, and they make it structured, predictable, and incredibly efficient. But, and this is important, that specialization is also their biggest limitation. A heap is terrible at finding some random item in the middle. You can't just ask it, hey, where's task number 582? You'd have to search the entire thing. They solve one problem, finding the most important thing, but they do it better than almost anything else on the planet.
So let's bring this all home. After everything we've talked about, what's the one big idea, the core insight that you should really take away about heaps?
It's this. Heaps don't care about order. They only care about importance. So stop thinking of them as some weird kind of sorted tree. Instead, think of them as a finely tuned machine built for one single purpose, to relentlessly and with incredible efficiency track what matters most. They're the ultimate proof that to find number 1, you don't actually need to know the order of numbers 2, 3, 4, and 5.
So here's a little something to think about. The next time you click on something and the response is just instantaneous, or your video call stays perfectly smooth even while you're downloading a huge file, just take a second, because there's a really good chance that that seamless, instant experience is being powered by one of these clever, efficient, and beautifully pragmatic structures working away silently in the background.